So we spent
Or did you get a video?
quite a few lectures go through those electron motion in hydrogenic or hydrogen-like. I want you guys to be very careful about the model. The model is only discuss about one electron, right? So therefore, you're referring to hydrogen atom, or you have an ion that only have one electron system. Now, exciting after we learning all of this. Why am I doing all of this, right? But because those are really the wave function for the atomic orbital that we know when we learn from atomic chemistry. So the atomic orbital is one electron wave function in this atom. So therefore, whatever we learn for this electron in hydrogen atom that define the wave function for specific atomic orbital. Now we know that wave function have three quantum numbers because you only describe the electron motion with respect to the nucleus, so therefore you only have one position vector here, and this position vector only for the electron, right? So the solution for the wave function really refers to the electron. So if we want to do a square modulus, so the probability density, when you look at the probability density, right, for this case, the system is the electron, so therefore the probability density to locate the electron, and that is really indicate the electron density, right? So now those are atomic orbital wave functions. All right, now we can have a lengthy discussion a little bit. So you can describe those atomic orbital by writing out the wave function like this, or you just have a notation like this. Because once you figure out those three quantum numbers, you will define the exact wave function. So either way, it is fine. So basically, if we say this is describe the electron can be described by a particular wave function, then we say the electron occupies that particular atomic orbital. All right. Now, in the wave function, we have three quantum numbers: the n, l, and m sub l. Right. So through solving the Schrodinger equation, n is the principal quantum number. It can take negative, it's positive integers, and then n will restrict the value of l. All right, now l will start from 0, and then 1 and 2, and keep going. The largest one is n minus 1. That's how you can tell the principal quantum number restrict the value for the orbital angular momentum quantum number L. Now, how many values of L you can have? You're going to have n values of L. As you can tell here, it's starting from 0, integers, go all the way to n minus 1. All right. Then we say, okay, you have an orbital angular momentum, orbital motion. We can refer to the motion in the z-axis, and this is the z component. The z component of the angular momentum quantum number, because angular motion can be in x, y, z, and we're interested in the z-axis. Of course, it has a specific name. We know this is also called a magnetic quantum number. So the L will restrict the value, quantum number value for m sub L, and we said it will start from the negative, it ends at the positive. And then what you have is you have a step 1, goes through the 0 and go all the way to L value. So the m sub L is also a part the integers. Now, how many values of m sub l do we have? We will have 2l plus 1. The quantum number for m sub l will have 2l plus 1, so the value will be restricted by l. Okay, now, if we dive in, those three quantum numbers, the principal quantum numbers really give us the indication of the shell, as I mentioned. So you can have an orbital in the K shell, L shell, and M shell. So basically you can refer to with the number, or you can use the letter. This needs to be capitalized. When n equal to 1, principal number quantum 1, then the electron is in the K shell. And if n equal to 2, you can also in the L shell, then M and N, right? So you can keep it going, and that's fine. But typically we deal with the system, into the shell 4 of N is pretty large. Okay, now after the main shell, because N, you restrict the L. L going to form, so this is your shell. Then L is going to form the subshell. Alrighty. Now the subshell represented by the quantum number L, or you can have a letter. We're very familiar with those. When the L equal to 0, that is your S orbital. When L equal to 1, that is your P orbital. Those are lowercase, right? When L equal to 2, that is your D orbital. Now, of course, L can equal to 3 and 4, so on. When L equal to 3, what orbital? S, P, D, F. Very good. So on and so forth. Right? So, under each shell, you will have subshell. Then afterwards, then you have the orientation in the z-axis, and it's not the same. That is different. Okay. All right. Now, this is it. We can write out this table can clearly show you, under the relationship. This really can link, guys, the what you learn from Jenkins, right? So I always said physical chemistry is relearning of Jenkins. Except when you're learning your Jenkins, you're told that's what it is. But in physical chemistry, we tell you why this is like that. All right. Okay, so now here we go. This is probably more conceptual, more easy to read. You have n principal quantum numbers, start with the integer number 1. In that case, L only gonna have one value. Then the m sub L only have one value, that is 0. Okay, do you have a question with that? So this will be your K shell. That is your S orbital. Then if you know the m sub L value, you know exactly what the wave function for that orbital. Now what that orbital is, guys? So you will have n equal to 1, L equal to 0, m sub L equal to 0. So you can represent that electron orbital by 3 quantum numbers, that will be 1, 0, 0, or you can represent it by 1, 0, 0. Or you can write out in terms of orbital, so n equal to 1, then the orbital L equal to 0, that is your 1s orbital. Right, are we all good? Yes? Okay, all right. And then we can keep going. So when you have n equal to 2, then you have 2 values of L, 0 and 1. When it's 0, represented by S orbital. When it's 1, represented by P orbital. That's why when n equal to 2, L k equal to 0, of course, m sub L only going to have one value. So that is your 2s. All right, then you're going to have n equal to 2. L can also take 1. then M sub L can have 0 plus 9 minus 1. You will have 3 M sub L values. Then what is atomic orbital, guys? 2p. It's all good? Because the atomic orbital can be represented by N and your quantum number L. So 1s, 2s, 2p, all right, okay. And then after that, then you can have you can write it out, right? So this is your 200, 2s, then you have all those 3 2p orbital. Then you may ask, what kind of p orbital are you guys familiar with? The 2p. Oh, when you guys populate, let's say, what do you guys like? Do you like a carbon pattern, nitrogen pattern, or oxygen pattern?
Carbon.
Okay. Carbon pattern? Okay. Alright. Now I want you guys, do you guys sound familiar? Carbon has how many electrons?
6.
Ooh, how many electrons? We may have 4 valence electrons, but total number of electrons? 6. 6 electrons. 4 valence electrons, so you are correct in that perspective. Alright, so 6 electrons. How do you guys do it in Gen Chem? When we say, can we populate those 6 electrons in the atomic orbital? How do you guys do it?
1s2.
I think you guys have like, you gave me goosebumps, like those bracket. Is it like that? Some sort of this.
Oh yeah, and then the space.
It's some sort of this is some three.
We're just
At
fine.
least that's one way of doing it. Is that true?
Yeah.
So
Yep.
what do you guys have it here? 1s, right? And with 2s here, what do you have it here? 2p. So why do we have sections of 3 in the 2p?
It holds it at 6.
You guys didn't tell our Gen Chem teacher or your high school AP teacher did not tell you X, Y, Z?
We've done
Oh, okay, then I need to talk to my department head about this. Right, there's a three, so P has X and Y, Z, right? Okay, alright. Now what we have here is P has -1, sub-0, +1, and we will show how this will be linked by the Px, Py, Pz. Okay, alright, so we will follow that one up. Okay, now we can keep it going. So then n equal to 3, then you will have a total 9 atomic orbitals. Within that, you would have the L equals 0, 1, 2. So therefore, under the M shell, you will have a S, P, and D orbital. So you have a 3s and 3p and 3d, and that's how exactly we learn in Gen Chem. Okay, so let's keep going. All you can work in a diagram like this, right? That's what we get used to. Is that you have a y-axis is your energy, and then you have an energy for each of these orbitals, and then we use a line just to indicate the energy values, right? So, alright, so we can draw an energy diagram. That is energy for the electron in the hydrogen-like hydrogen atom, hydrogen-like system, which are ions, only have one electron. Alright, now we can label it, refer to the quantum state. Why not? Because the energy for a particular system, if I really want to write out, is a negative and a constant divided times the z squared over n squared. So you know the relationship. The relationship for electrons in this hydrogen-like system, it is a negative value. Also, it's proportional to z squared. So for a particular atom, z Z is a constant too, only you compare with two different systems. So therefore, it's an inverse relationship to the n squared, but it is a negative value. What does that mean? The smaller the n value is, the more negative the n value is. That means the more lower energy that it is that's the algebra. So therefore, if we look at when n equal to 1, you only have the 1s atomic orbital. And that relationship tells you this one sits at the lowest value. Now, when n equal to infinity, that is the energy equal to 0, that is your highest value. And between 1 to infinity, that's you're going to populate the rest of the energy state. So therefore, when you have n equal to 2, how many atomic orbitals do we have? 4. Excellent. What do we have? We will have 2s. 2p has 3 of those 2p's. Do you guys agree? Does that make sense? Alrighty, now this takes a shortcut. Let me show you where the shortcut is. Here, 2s. Look at that. It indicates only 1. Because indicate the m sub l equal to 0, you only have a 2s, nothing else. Here we have a 2p. It has a shortcut. The reason I say it has shortcut, it indicates what? There are 3 of them right there. Alright, so you could just write it out. 1 and then 2 and 3 regarding sub 2p. Alright, now 2s and 2p, do they have the same energy?
Well, yes. Yeah, they do.
2s, 2p, do they have the same
Yes.
energy?
Yes.
Okay, good. It wants to give you 2s, 2p, do they have the same energy? Now how do we know they have the same energy? The energy expression only depends on what? The n. So therefore, 4. But I know why some of you guys shaking head. Because what is the model for this? What is our model? It is only one electron. How many times we come across system only for 1 electron? Look at the carbon. Look at the carbon. How many electrons do we have? 6. 6. So when you look at those, multi-electron atom, it's no longer true. It's no longer true to get to you. It's no longer true. The 2s energy will be the same as 2p anymore. Alright, however, under the assumption for 1 electron atom, that is true. So we will talk about this. So I know some of you shaking hands say, no, 2s and 2p, they are not the same energy. It is true. We'll come back to this. But this is when you refer to the multi-electron system. But for 1 electron system, under that assumption, then the energy we derive only based on the principal quantum number n. Alright, okay. Alrighty. Now let's dive in. Now we know you're going to have shell, subshell, you're going to form atomic orbitals that define by n, l. Alrighty. So one of the atomic orbital we are very familiar with an SPDF. But we're going to go through S and P, and a similar idea you can use to understand the rest of the atomic orbital as you come across. Alright, so now we say S orbital. From the, what you have learned, What is the shape of the s orbital?
Sphere.
Spherical, right? How about p orbital?
Pebble.
Dumbbell, right? It's a dumbbell sits along those three axes, x and y, z. Now we want to show, learning all of this. So when it's spherical, we want to show from our quantum mechanics and tell you why you will be told it's spherical. Now we prove to you it is spherical. All right, so if we look at the s orbital, give me some s orbital that you would like me. Huh? S orbitals? Then generically I will have n s. Is that true? Because each shell has an s orbital. So therefore, generically, you use ns to represent, which include 1s, 2s, 3s, and so on and so forth. Right? Just that to clarify here. Now, if I want to use one of them as an example, which the simplest one we can come up is as an example, I can use the 1s as an example, right? 1s. Also, the 1s is really our ground state as well. Not only the example for the s orbital, it's also the ground state for all the atomic orbital. All right. Now, if I say the ground state, the 1s, the immediate thing what you guys can pop up is, do I know the exact expression for this wave function? Because once I say 1s, I know right away the three quantum numbers will be 100. Once I know it's 100, boy, you guys are all very good at it. Can we come up the exact expression for that 100? Where are we? Is that what you're looking for? Is that the table you guys are looking for?
Mm-hmm.
And we spent half of the lecture today as well, Friday, on Wednesday, to derive all the properties regarding this 100. So I'm gonna go write it out, this one, and you guys are gonna tell me if this is good or bad, okay? Yeah. Did somebody say bad? Have no confidence in your lecture? Yes or no? Is that the wave function? No, I don't need you guys to remember it, but you know, as long as you know how you get there. All right. So this is your wave function. Now, a sub 0 and a, they can be converted. Looking at hydrogen, if I'm looking at a hydrogen atom, a sub naught is equals close enough to a, so you can use either one, it's fine. So this is your wave function. Now, mathematically, I don't want you guys to read the slides. If I give you this mass function, can you look at the relationship of the function? So what is our function right here? If you look at that's why the beauty of the math is outstanding, because you have a mathematical equation, you can derive so many statements. That's why I like math a lot. Because if you think about it, I have a function here for this wave function, right? So that will equal to a constant times the e function. This is an exponential decay. This is your function, and this is our wave function anyway. So if I take a look at this, and that actually depends on r theta and phi. So what does that mean? That means, what does that mean? Don't worry about if it's a quantum mechanics. Just like give you this particular function, what can you describe? Yes?
Will it decay as we increase the radius, so it should be farther?
Okay, so the value for the function decreases. Excellent. So therefore, the value, very good. That's one of the conclusions. Decreases with the increase of R. You guys agree? Okay. Now the R is from 0 to infinity. So that means this wave function, or we just write out our wave function, the max will be at or equal to 0. Okay, very good. Now let's do a step further. How about the square of that, square modulus? What about the max?
It's the same.
The wave function has a maximum value of 0, and that wave function is a real function. It's a real function. So the square of the real function, the max, also at 1 are equal to 0. Alright, now when r equal to 0, what would be the value of this wave function? That really equal to the constant. So that is all pure mass based on the relationship, that one as described by this particular wave function. Excellent. That is one of the conclusions that we can draw. Any more? Based on this mathematic formula, any other conclusion you guys can draw? Although this particular function looks like it's a three-dimensional system, but however, effectively only depends on the radius. So what does that tell you? That tells you that all values of theta and phi, as long as r is the same, what do you have? I'm just thinking through on my mind and writing down the board. Right, so basically, a specific R values, let's say I'm the nucleus, our system is that electron orbit around the nucleus on model. So at particular R value, the radius from the electron to the nucleus, does not matter what the theta and the phi angle is. The value for the wave function is exactly the same, equal to one particular value. Okay, that is why the s orbitals are spherical, or s orbitals have spherical shape. So now you have been told, from our GenChem teacher, or maybe your high school AP teacher tell you, okay, just remember, the S is a spherical, blah, blah. Now you can tell your friends and teachers, after learning from quantum mechanics, you tell them why it is spherical, right? And the exact mathematic expression for it. Any questions on this one? Okay. All right. And then, of course, you can calculate the value. I'm showing you here the energy expression. And we use a hydrogen atom as an example. And then you can even calculate many other values. Okay, yes?
Is that only for when L and M sub L are 0? So when S and sub S? You use 2P and then U or 1 and 5 and theta?
So, I think it's for the L and M sub L equal to 0, most of them. Okay, so you can look at it has to be the constant, right? The angular component of the wave function is a constant. That's why the total wave function only depends on the variable for R, because the total wave function is a product of the radial component and the angular component. So for that to happen, you have to have the angular component to be a constant. So if we go back to our equation here, if you have the 0, 0, that is the constant. So therefore, at any radius, as long as the radius is only the variable. Once you have fixed the radius, the angle component is a constant. But if you look at L equal to 1 and M sub L equal to 0, this is no longer the case anymore. Okay, so yes, it's only for the L and M sub L both equal to 0, and the angular dependence vanished. All right. Now, we say in quantum mechanics, as I have mentioned, let's get back to the postulate. So if we have a wave function, what is the significance of that wave function, guys?
Tells
Do you
us
have a
everything.
significance of that wave function?
Tells us everything
What do
about
we
the
call the
system.
wave function? We call it is what? It's a function. We call it a wave function to acknowledge the particle wave duality, but the value is just really the amplitude, right? Now, what is the significance in the wave function? Does not reside in itself. It resides in the square modulus. Very good. Now, what is the significance in that?
Probability density.
It gives you the probability
Density.
it is a probability density. So therefore will allow you to figure out the probability to locate that particular particle at particular point of space. So knowing the probability will allow you to locate right at one position. Okay, now how do we do that? So the probability at particular point equals to
Square modulus.
the density and times
D tau.
density times the small volume at that one location. How do we represent small volume?
D tau.
We use d tau. Okay? Now d tau could be one-dimensional, substitute the volume for one-dimensional, could be two-dimensional, substitute with two-dimensional, or three-dimensional. Alrighty. Now, let's say, okay, for our systems, those are atomic orbitals. Now, if I want to write out